Hello everyone, how are you? I hope you have gone through our last two recorded discussion. So we were talking about corrosion measurement, and in last discussion we have gone through how we can use the microscopic tool to analyze the corrosion and corrosion related product. So in that discussion, we have talked about scan electron microscope, transmission electron microscope, atomic force microscope, etc. Today we are going to talk about basically spectroscopic tools that can be utilized to analyze the corrosion product. So few of them can be named as X-ray diffraction, so commonly known as XRD, or Fourier transform infrared spectroscopy, FTIR, Raman spectroscopy, and X-ray photoelectron spectroscopy. So the name is, I think, already well known to you. And if we utilize one of these data or maybe a couple of these techniques together to analyze the corrosion product, then we can get some good information about corrosion and what kind of product is formed after corrosion. But still data is not very sufficient to get very conclusive idea. Therefore, along with these analysis, we have to also go through some other technique analysis. So if we club all these data, then we can at least reach toward a more appropriate answer. So let's say we start with X-ray diffraction pattern. So we are already familiar with the technique, and technique is based on the diffraction of X-ray from the lattice of a material. So as we know, the wavelength of X-ray is almost in order to the spacing between the lattice. So X-ray can be easily diffracted from the lattice fringes, and it can create a well-known pattern. So each material has a unique crystal structure. Therefore, for each material, we can have a very unique X-ray pattern, right? So if you know this system work on this formula, the formula is n lambda is equals to 2d sine theta, where d is the lattice spacing and lambda is the wavelength of the X-ray. So what kind of information we can reveal if we use the XRD analysis of a corrosion product? So if we go for this, so as you know, this is a very fast, within 10 or 5 minutes you can get the data. So rapid method easily provide information about the phase or the composition of solid material. Moreover, the identification of phase composition, even if as opposed to the elemental composition, is crucial for the understanding of corrosion process. Means within the material, if you know maybe the material is only iron, but it may exist in different phases. So, and each phase has their different corrosion resistance. So if we can identify the phase composition, then it will be easy to understand the corrosion process, and that we can do just doing the XRD analysis. Example, let's say if you have a iron and which is corroded, so corrosion product may have the mixture of magnetite, that is Fe3O4, or geothite, that is FeOOH, or maybe ferrihydrite, so Fe5O7OH, and some water. So these can be easily identified and sometimes quantify also by using the XRD analysis. So even within the iron rust, we can have an idea what kind of composition or phase composition is there. So even there is also some very microscopic tools, sometimes we call it micro XRD, that is even better to analyze a very small region. We can say micro scale region can be analyzed, and we can get a very good information. So XRD is one technique, and if you see the data, So it looked like something this. I think you already have here. So the x-axis is basically having the 2 theta, that is the angle, and here the intensity, that is the arbitrary unit. So this is the only one pattern which is the XRD data of iron rust. So if you see within this data, we are having a different XRD peaks, and which is almost correspond to these three different phases. The star, this is Fe3O4. You can see these stars here, this point, then this highest intensity point, this point, and this point. Similarly, the dot correspond to Fe2O3, and many points are the same in case of Fe2O3 and Fe3O4. Only one or 2 points are different. Let's say this is the 1 point. Similarly, this is the Fe2O3 point. So means they're both Fe3O4 and Fe2O3. Both the kind of phases are there. Also, if you see the plus sign here, independent plus sign, then this is the plus sign, this is the plus sign, this is a jointly, and which correspond to alpha FeOOH. Means this phase is also present in the rust. So the rust was mainly composed of Fe3O4, Fe2O3, and also some part of the FeOOH, or the some portion of the alpha FeOOH is there. So by doing XRD analysis, we can get this kind of idea. Now move to the next technique, which is FTIR. So FTIR is very powerful tool to identify what kind of chemical bonding is present. So you know if there is a change in the material phase or the material composition, then of course there would be a change in the chemical bonding, and that kind of analysis we can do by analyzing our corrosion product through FTIR. So even we can say like the FTIR data give a fingerprint of a molecule, right? And in this technique, basically we use the basically the light which is having different frequencies, and if that light interact with the material may absorb some portion, transmit and reflect. So any of the data can be collected, and then its Fourier transform can be reported in form of spectra. Maybe you can see this kind of structure where we have output split kind of mirror, and in FTIR spectra, collect and digitize the interferogram, perform the FT function, and then display the spectrum. So this is the whatever is in the system, and once we see the FTIR data, we can get the variety of information, such as we can quantify some component of an unknown mixture. Means not only just qualify, we can give the quantitative analysis of unknown mixture. That is very important point. Similarly, it doesn't matter whether our sample is solid or our sample is liquid or it's in the gas state. Means in all state or all kind of sample can be analyzed by using FTIR analysis. Absorption band in the range of 4000 to 1500 wave number are typically due to the various functional group. Means if you see the plot, in x-axis we generally plot the wave number, and in the y-axis we plot the intensity, whether it's a reflection, absorption and transmission mode. And if we see, so in this range 4000 to 1500, generally we give the peak correspond to various functional group. Means if functional group such as OH is attached with your material, or C double bond O is there, or NH bond is there, or CS3. So these kind of functional groups are there. They generally come in between 4000 to 1500. So if any functional group is there, we can easily identify by doing the FTIR analysis. See, similarly, in lower range, which is basically 1500 below to 400 wave number, is particularly referred to the fingerprint region. Fingerprint means belong to a particular element or material, and more a kind of intramolecular phenomena. So this you can divide into two regions, like higher than the 1500 side and then lower than the 1500 side. So higher than the 1500 side, we are going to get the idea about functional group, and lower than the 1500 side, we can get the idea about the what kind of element is there or what kind of molecule is there, right? So this information we can get by FTIR analysis. Even we can also identify the chemical from, let's say, something is spills or some paint is there, or polymer is there, or coating is there, a drug is there, or any contamination is there, and you just want to identify what kind of chemical is there. So the easiest way, do the FTIR analysis. Let's say you have some paint and you are not aware what kind of composition is there or element is there. Just do the FTIR analysis and we will be able to get the idea about the chemical composition. So this is very good technique for corrosion also. Here you can see one data, the FTIR spectra of the corrosion product of iron. So iron you have already seen earlier, like XRD data, what kind of peaks are there. So similarly here you can see the variety of peaks are there. See, they started just from 2000 to 500. Why? So it depends upon our choice. If you are interested about functional group, then go beyond 1500. And here they were just interested about the molecular structure or what is the elemental phase is there. So they just perform the analysis from 2000 to 1500 and see the peak as 500, and they are designated at delta FeOH, means delta kind of FeOH. Similarly, the peak here, which is almost 900, alpha. Similarly, at 1050, almost gamma, and then FePO4, 2s2O. So these peaks correspond to a different phase of iron hydride. So in presence case of gamma FeOH as this value, alpha at this value, and FeOH delta on these values. So by just doing FTIR analysis, in this sample we can have the idea what kind of different alpha, beta, gamma phase of the FeOH are there. The another tool is Raman spectroscopy, and sometimes we call it a complementary unit of measurement of the FTIR. Here again we have a very focused incident light. So generally we use a laser light, and the concept of the Raman is such as, let's say a light is interacting with a material. So of course we know there is a possibility like it may absorb by the material, it may transmit by the material, and there is also possibility some percentage of light may scattered from the material. So Raman has analyzed these things, and Raman sir has proposed like or investigated and then reported that in the reflected light is not having the same wavelength as the incident wavelength. There is some change in the wavelength. Sometimes this wavelength is higher or lower. So depending upon the higher or lower, we can say Stokes or anti-Stokes lines. And so basically what we are observing a shift in the wavelength, right? And this shift is the characteristics of the material, or it depends upon the nature of the material. So if we are doing a Raman spectroscopy and we are monitoring the shift in the Raman peak, then we can identify what kind of material it is, right? So basically scattered light is used to measure the vibrational energy mode of a sample, and the system is contactless and non-destructive also. The thing is going to happen, just you are going to strike the light on your sample. So again, this technique is very useful, similar FTIR. Here we can get a variety of information, and it provides both chemical as well as structural information, and we can identify the substances or the material through their Raman fingerprint. So again, this is the kind of fingerprint, means give the exact final output about the material. There's no doubt. Here again, whether your sample is gas form or liquid form or solution or solid or crystal, whatever, we can measure it by using different sample holders. Here again, we can identify an unknown material, polymorph, and if there is any change in the molecular structure, that can also be identified. Like during the process, if there is a change in the material properties, that can be identified, or if there is any change in the crystalline properties, that can be also traced out. So it's very good. And see, as you know, this Raman shift depend upon the phonon movement. If there is any kind of stress in the system or stress in the lattice or a crystal, then we can easily identify. So we can evaluate the magnitude of the residual stress, assessing the direction of orientation of the molecule. That can be also identified. So high spatial resolution up to some micron scale can be even identified. Means you can make your spot very small and you can identify a very micron size area, not like a big spot in the sample. So this is also one of the good technique to analyze the corrosion product. And here we can see one example to understand the Raman spectroscopy data. And this paper recently published in NPJ, Materials Degradation, in 2018. The title is Kinetics of Pipeline Steel Corrosion Study by Raman Spectroscopy Coupled Vertical Scanning Interferometry. So basically they use two systems. One is Raman spectroscopy and other is basically Raman spectroscopy is coupled with vertically scanning interferometry. And what is the steel pipeline? And they are going to study the corrosion kinetics. So in this study, a concept for the characterization and the quantification of corrosion is demonstrated on API X70 steel. So this is the material, steel, which was immersed in 3.5 weight % NaCl solution. Okay, so what was the data? So I'm not going to talk about detailed experiment. If you are interested, you just follow this reference. I would even suggest you just download this reference and read it to get the more clear idea about Raman spectroscopic analysis in case of corrosion product. So here is the data. They basically observe the formation of a pit, and if you see this blue color, this is the region of the center of the pit, and in the second figure, if you see, this is the region of outer surface of the pit. So even by Raman spectroscopy, they are able to see the difference in these two. See the first figure, the Raman shift is something else. The intense peak is at 673, while in case B, when the measurement was taken at the outer surface of basically the outer side of the pit, we are able to see the peak at 253 and 1305. So these two things are different. So what it indicates, it basically says like, though this pit formation is similar, but the corrosion product, whatever form at the center of the pit, is different as compared to the corrosion product form at the outer surface. So see, whatever peaks positions are there in this case of first measurement, they are reporting at 673, 254, 314, 540 centimeter inverse. So all these are basically correspond to magnetite phase. Means Fe3O4 is present at the center of the pit. But the peak positions in sample second are coming at 253, 280, 529, 658 and 1305 centimeter. And that is something else. This is basically a lepidochrosite, which is kind of gamma FeOOH. So now you can just see by doing Raman analysis as two different positions. we can say even the same pit is not having the same corrosion product, right? So Raman spectra of the magnetite occurs mainly in the middle of the pit as indicated by the blue Raman map, while Raman spectra of Fe hydroxide found especially around the pit and in yellow Raman map. So this is one idea like how we can analyze the Raman data. And our last spectroscopy technique is XPS, so X-ray photoelectron spectroscopy. So I think let me just give a brief idea about this mechanism. So if we have a photon source and this light source is interacting with the material, then and if it is in a very high vacuum, so XPS generally work in very high vacuum, 10⁻⁷ bar or something, maybe even slightly higher than that. And once the photon interact with the material, they basically there is a chance like valence band electron can get also excited, and even inner side electron can get excited, and then we get the photoelectron, and then by the detector we detect the energy and count of the photoelectron. So if we count both the things, energy and the count, and so by irradiating a material with a beam of X-ray while simultaneously measuring the kinetic energy and the number of electrons. So since we are using X-ray, that's why we are able to excite the inner cell electron, and that are highly binded with the system. So if we want to calculate the binding energy of that particular electron, so it can be easily calculated. We already know the E photon energy of the X-ray photon, and if we can measure the kinetic energy when they basically ejected from the material, so already detector is there which is measuring the kinetic energy, and then one is phi is there, is basically a work function of the metal, or what is the detector based on the detector and metal. So it's depend on the both the spectrometer and the material. So if you know this, so this is a kind of constant value, or we can just have a fixed value for this. So if you know these two value, photon energy and kinetic energy, the difference of this can give the binding energy of that particular material, particular electron in the cell. So that is very good information. By just plotting the binding energy with respect to the intensity, we can get very clear cut idea what kind of material it is, and many other information. Maybe I can just summarize here. So we can get the quantitative surface chemical analysis. Quantitative means exactly the number of elements or the amount of element. So we can estimate the empirical formula. Empirical formula means like what is H2O. So there's 2 hydrogen and 1 oxygen that you can identify by doing the it's not Raman, it's XPS. Sorry, I forgot to mention here. So in XPS, we can get the elemental composition. Here also the chemical state. So elemental composition means mixed material, what are the elements are there that we can identify quantitatively. That's very important point here. Chemical state, like whether they are in the chemical state, let's say charge 1, charge 2, electronic state of element on the surface. So here one example is there. We have again the iron rust and perform the XPS analysis. So you can see the x-axis we are having the binding energy in electron volt, and y-axis the intensity or the count. Okay, so this is the red peak. This one, if you see in all case, this is the actual data whatever we receive from the XPS. Okay, so this is Fe2 P3 by 2. So you know the Fe2 P3 by 2 orbit, and we are getting basically the energy of that electron. Electron is coming from that orbit. So high resolution spectra of carbon steel, and this 4 sample, this sample 1, 2, 3, and 4. 4 basically are the 4 rust when the iron was exposed in 4 different medium: stearite, M.F. T. special, and mixed consortium medium for 11 days. You just go through this reference. So you can get the detail about this system, but we are not having much concern about this medium. Our concern is, so let's say when the medium is different, it shows there is a difference in the corrosion product. If you see the data, see the first case, if you see the peak position and the shape of the peak. So how you can get that idea? So again, basically they have deconvoluted the peak. So they have fitted 3 different peaks. One peak is correspond to Fe2O4, another peak is Fe2OH, and third peak is Fe2O3. So within the one, so that was peak basically overall, and let's say within that system, 3 kind of phases will be there. So therefore, we are not getting very symmetric peak. Asymmetry means there is a different kind of bindings are there, right? So they have fitted it and correspond to their area covered with this fitting. We can say this is the percentage of these different phases. So within the rust, 1 phase, 2 phase, 3 phase can be quantified based on this area. See here, this is high, basically higher side. This is in the lower side. See this peak fitting, but this is again very much high. This is low. So when your iron is exposed in these 4 different medium, there is a differences in the corresponding phases, and they have summarized the data here. If you see these 3 components, Fe3O4, FeOOH, Fe2OH. So this is the electron volt. This is the position. So they fitted at 7, 10.15, 711.5, and 712.8. So when medium 1, medium 2, medium 3, and this is the medium 4. So mix means 4 medium. So there is a 4 sample, 1, 2, 3, 4 sample. So see, Fe3O4 is highest in case of third sample. FeOOH is highest in case of second one, and Fe2O3 is highest in case of second one. So that can give one idea, like if there is a change in the medium, there is change in the corresponding phases. So that we can analyze by doing the XPS spectroscopy or XPS analysis. So there are more other examples. I would suggest you should go for other examples and read 1 or 2 other research articles. Now the next topic is corrosion measurement by third technique. So we have gone through the one which was on about how we can analyze the corrosion and corrosion rate by weight loss method. We have discussed in detail how we can do the weight loss. Then the second was surface analysis. So second we talked like if there is a change in the surface, how we can analyze. So either by using microscopic technique or by using spectroscopic technique, we can analyze the changes happen at the surface due to the corrosion, or we can also analyze the corrosion product, right? But if we are thinking more quantitative information and more logical information and analysis of the corrosion, some other technique need to be explored. So in the same directions, we are moving toward the next, that is electrochemical technique for corrosion measurement. So this is the, I think, the most studied technique and also very much convenient for us. We are already familiar with the electrochemical measurement and technique. And even if you know, our corrosion is itself an electrochemical cell. So all the corrosion is basically happened due to the formation of electrochemical cell, or corrosion is an electrochemical process. So therefore, here in this third one, we are going to put a lot of emphasis, and we will go through each and every point very slowly. So why we are going to use this technique? I think I have just mentioned 3 points here. advantage, the technique is very, very sensitive. So even the things which we missed out by our previous two methods, let's say there's not very significant change in the weight, maybe you're not having that much time or things to wait to get the idea about the corrosion. And sometimes if you don't have the access of a sophisticated instrument like XPS, XRD, TM, UV, and FTIR, Raman, all these. So this is the one best method in which we can give very sensitive data, and even we can identify a very slow corrosion, right? Another point is short experimental duration. Here within hours or even sometime in minute we can get the data of corrosion, while in other cases you have to wait for sometime days, sometime month or years also. And the third point, see, we have already gone through the electrochemical or electrochemistry analysis, and the electrochemistry is a well-known topic. The fundamentals are very much established, so each and every kind of analysis can be easily performed and can be understood, right? So therefore we are going to focus in the electrochemical technique for corrosion measurement. So let's go to this section. So electrochemical. So as I told, we can get a very good quantitative analysis of the corrosion, but mostly in case of general corrosion or a galvanic corrosion. So if there is a galvanic corrosion or a general corrosion, then we can get quantitative idea. But if there is a pit formation or a crevice corrosion, or we can say the localized corrosion, then we may be able to get the qualitative data, not exactly quantitative data. So if you talk about the electrochemical nature of the corrosion, we are already familiar. Let's say if there is a metal surface, so at one region it forms the anode, and this anode basically emit the ion of the metal. So there should be something which can create an electrolyte or maybe anything that can provide a path for that ion. And then the other surface of the same metal may form the cathode. And so internally you can say there is a transfer of electron. So that's current path. So basically overall it forms an electrochemical cell. So this is the overall principle of the electrochemical corrosion. So there are four elements of the corrosion process, you can say. There is an anode, there is a cathode, there is a path for ionic conduction, so you can say electrolyte, and there is a path for electron flow, you can say the current path of the metal. So in generic, what is happening, if a metal is oxidized, if it loses the electron at the anode and the process is, then we can say the process of corrosion is happened. So let's say if M is the metal which is basically which lost the N electron, then it gained the N charge, positive charge, and it become the M plus N ions, right? So these were the basic fundamental, but how do we do the electrochemical measurement? So now let's switch here. So see, based on the current applied, we can divide our measurement basically in four categories. So one is DC current measurement. DC current measurement, those measurement in which we use the DC current or a direct current, and the methods are known as linear polarization technique, TEFL, extrapolation, or open circuit potential versus time measurement, OCP. And if we use the AC current for measurement, then the well-known technique is impedance spectroscopy or electrochemical impedance spectroscopy. We call it sometimes EIS. So these four techniques we are going to discuss for electrochemical measurement. So since first one is the polarization technique, I would just like to share a few points. What do we mean by the polarization or electrochemical polarization? So you just recall the things like you have one electrochemical cell, and you have two electrode, let's say a metal electrode. One, you immerse the electrode in electrolyte. So electrolyte your corrosion medium, right? When you immerse this electrolyte, some reaction is happen. So what is that reaction? So basically, when a metal immerse in a solution or contain its ion, sometimes a solution or sometimes also the metal is, so I'm taking the both the scenario. When metal is immersed in a solution or metal immersed in solution which also has the ions of the same metal. So these are two separate things. Just making together. Otherwise, just make one. You have a metal immersed in a electrolyte or a solution. So what will happen? Metal lose the electron to become metallic ion, right? Oxidation will take place. Similarly, if there is metal ion in the solution and other electrode, so there's two electrode, anode and cathode. So if the other electrode, then there will be deposition of metal, both you know. So maybe gain of the electron become the solid metal atoms. So doesn't matter whether we are having anodic process or we are having a cathodic process. I'm just considering the both. If both are there, once you will start this experiment, let's say only one cell, if I'm talking about, you just immerse, electron is eject, basically loose from the material, and then it's become the metallic ion. What will happen? So at the interface, we will achieve the equilibrium, right? After some time. Earlier, there will be a difference in the chemical potential. The chemical potential of metal will be somewhere here or here. Similarly, the chemical potential of electrode will be up and down. So after some time, they will become equal. So we will call this become the equilibrium condition of the metal solution interface. And then mu solution will be equal to the mu electrode. If that is the case, then the net current is zero. There is no electrode potential. The system is having perfect no current. The rate of oxidation and reduction reaction become equal. So the system is there. One side, whatever oxidation happen, the same time reduction is happened. So both the things are equal now. In that case, the equilibrium potential is known as T equilibrium. So this is the condition of equilibrium. But now what is the meaning of polarization? So think a little bit beyond. You form that cell. Now your mu solution is equals to mu electrode. What will happen if we just give some very small amount of, let's say only 10 milliampere or even less than that, very small current to the electrode? What will happen? If we apply a very small amount of current across the electrode, then it creates a potential across the electrode. Is it not? Right? So, due to application of external additional current across the voltage, we create a polarization. Basically, earlier it was equal, now it's become polarized. So, anode and cathode is not at the same potential. So, that is known as the electrochemical polarization. So, let me say here, if there is a change of potential, right, due to change in the intensity of the current passing through a working electrode, is known as polarization. If you are applying a current, then of course the current will flow through the electrode. So at the interface, some current will flow, and that flow of the current will create some change in the potential. So if that is happened, then we are calling the system is polarized now. So for measurement, always we have to think about the polarization, because we are talking about the linear polarization or the polarization based measurement. So we are not going to measure the system in equilibrium. We are going to apply some potential, means your system is polarized. Okay. So when a net current flow through the electrochemical cell leads to the difference between the potential E, then see, when we apply a current or some current is flowing, and if there is a difference in the potential E, then we can say how much difference will be there? equilibrium potential NEQ. So you see, E will be NEQ and plus something. Something is eta, or you can say that plus something is what? That plus something is the voltage after polarization minus voltage at equilibrium, right? So that is, what is that voltage? Basically, this is the voltage, extra voltage, whatever we applied, right? This is the extra voltage, whatever we applied to achieve the polarization. So we call it over potential. What we call it? We call it over potential or over voltage. So this is a very important parameter. What is the over voltage or over potential? And because in polarization measurement we apply a very small over voltage or over potential. So over voltage depend upon the current density, and when there is no net current flow, over voltage equals to 0, no polarization. So if cathodic current is applied to the electrode, the electron accumulate in the metal and the result of a slow charge transfer. This phenomena causes the cathodic polarization represented by NC, and it is always negative. So it is happening at the cathode. Similarly, at the anode, when electrons are removed from the metal. So when electron removed from the metal, it's at anode. In the case of anodic polarization, and the polarization is always positive. So means at anode the polarization is positive, and at cathode the polarization is always negative. And the net current that flow through the polarized system at any given over potential is I. That is basically the difference between the current pass through the anode and current pass through the cathode. If the same current passing from cathode, both the electrode, basically cathode and anode, then there will be no polarization. So if you want to measure the current which creating the polarization, so what is the difference between these two currents, right? And this is very well discussed by this Walmer, basically Bachelor-Walmer equation, fundamental equation in electrokinetics. And that equation is represented like I is equals to I naught in one direction, basically anodic, or you can say cathodic, minus I in another direction. So what is the overall difference they are just talking about? The direction, of course, will be different, and that will be equals to I0. So I0 is the current earlier when there is no voltage difference, exponential minus alpha C F eta RT minus exponential alpha A F eta RT. So these terms you already know. Alpha C F is you already know. Eta is already know. F alpha is basically, alpha C is the fraction of total free energy that decrease the energy barrier for cathodic reaction. So if there is a cathodic reaction, that create a kind of current. So what is that constant or fraction? And alpha A is basically 1 minus alpha C. So whatever is happening at cathode, just let's say overall fraction is 1. So if 40% is happening at cathode, then 60% will go to the anode. And F is of course the Faraday constant. So this is all about the polarization. Now we'll choose the how we can do the measurement. So today I think I would stop here. I already talked about 44-45 minutes. So today we just discuss 4-5 things. The first one was how we can use the spectroscopic tools to do the corrosion product analysis. Particularly how we can use X-ray diffraction technique, Raman, FTIR, and XPS. And then we move to the other very important tools, that is the electrochemical based corrosion measurement. So this is our third technique, right? The first one was weight loss, the second was surface by spectroscopic and microscopic tool, and then third was the electrochemical tool. So in electrochemical tool, we basically divided into two categories: the measurement which is based on the DC current, and the measurement which are based on the AC current. And in DC current, now we are talking about the polarization based measurement. So I just discuss what do we mean by the electrochemical polarization. And this is only when your system is not in equilibrium due to some applied current if there is any polarization in the electrode, then we consider we are having the electrochemical polarization. So thank you very much, and soon I will come with our next discussion.